Hello everyone, and thank you for attending today's webinar, How to Improve Characterization for Ebsd and EDS Applications. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you will receive an email later via email. We do capture all questions. A copy of today's slide deck is available in the resource list widget, which looks like a green folder. You can expand your slide area by clicking on the maximize icon in the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately one day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I would like to introduce today's presenter. Matt Nell is the Ebsd product manager at EDAX and has a passion for Ebsd and microstructural characterization. Matt joined TechSem Labs, known as TSL, upon graduation from the University of Utah in 1995 with a degree in materials science and engineering. At TSL, he was part of the team that pioneered the development and commercialization of Ebsd and OIM. After EDAX acquired TSL in 1999, Matt joined the applications group to help continue to develop Ebsd as a technique and integrate structural information with chemical information collected using EDS. Within EDAX, Matt has held several roles, including product management, business development, customer and technical support, engineering, and application support and development. Matt has published over 70 papers in a variety of application areas. He greatly enjoys the opportunity to interact with scientists, engineers, and microscopists to help expand the role that Ebsd plays in materials characterization. In his spare time, Matt enjoys playing golf and pondering if changing the texture of his clubs will affect his final score. Now over to Matt.
Thanks, Jonathan, for that introduction, and thank you. Good morning or good afternoon to everyone for attending. We appreciate it. Today I'm going to talk about how to improve characterization efficiency using EDS and EBS. Just as a quick introduction, I kind of jokingly put here efficiency as the ability to accomplish a job with minimum expenditure of time and effort. So basically what I want to present are features within our system, both hardware and software, that improves the efficiency for our users, makes things faster or make things easier. I'm planning to cover both EDS and EBSD, but with my background, I'm going to lean towards EBSD capability, but I'm aiming to show a little bit of both. And most importantly, this is not really a comprehensive list of things, but it's a combination of some new features that have been developed. We've developed a number of products over the last 12 to 18 months that really help improve efficiency, and also ones that I've commonly used in my work, both recently and over a longer term. I'd like to thank a number of my coworkers, Sean Wallace, Renee DeClos, Jens Raffleson, Sheng Mu, and Stuart Wright, for really years of discussion and work. And really I want to thank the hardware and software engineering groups here at EDAX for taking ideas and making them a reality. You know, as we use the software internally and externally, we find out what we need to make it easier, and those guys actually do it. I'm just a lucky one who gets to talk about it. So the first thing I'd like to highlight is EBSD camera speed. So this is just a little slide showing indexing speeds by year. And so when I started, we were going about 1 pattern per second, give or take, in the analog camera days there. And we've stepped up through digital CCDs, high-speed digital CCDs, and now high-speed digital CMOS cameras that have reached speeds of 4,500 index points per second. So obviously, if you can go 4,500 times faster, that's going to be greatly more efficient. And we do this with our new Velocity camera. We have the Velocity Plus and the Velocity Super. The Velocity Super is the fastest EBSD camera available. It's powered by a high-speed, low-noise CMOS camera. And in addition to being fast, it provides patterns of 120 by 120 pixels at those high speeds. So not only do we get high speed efficiency, But this increased pixel resolution provides I'm going to use the word higher quality, but quality is not really the right word, but we have more pixels to work with. And this pixel resolution allows for improved band detection, which follows for improved indexing performance and improved orientation precision at high speeds. So it's faster, but also with more data, which leads to more accurate, precise data. This is just an example from our favorite material, Inconel 600, a nickel superalloy, showing 3,000 index points a second. At these speeds, we can get indexing success rates over 99%. And if we push this to 4,500 going on, this is an additively manufactured material. The velocity super goes up to 4,500 index points per second. And this is 98% indexing on what we call more of a real world sample, not just a demo sample. So the camera is very fast. So that's one area we get some efficiency. On the EDS side, we have a number of detectors that are also designed to be very efficient. So we have our element detector, which is our entry-level system. That's there on the left. On the right, we have our Elite TEM detector. I'm going to focus on the two in the middle, the Octane Elect and the Octane Elite. These are both cameras that are detectors that are designed to work in integrated EDS and EBSD systems. The Elite can also be integrated with a WDS system. So these are EDS detectors that really combine well for efficient EDS detection, but also efficient simultaneous operation. So I'm going to go through a little bit of why that's the case. So our EDS detector, really what it comes down to is we have electronics that provide superior performance and superior throughput. So what you can see here on the chart on the left, this is a function of the resolution of the EDS detectors on the vertical axis, and the processing time is on the horizontal axis. So you can see there on the traditional detector, that's I'm colorblind, so I can't actually tell the color, but the curve that's higher, it looks kind of red to me. If we have a long processing time, the resolution is down in the 135-ish type range or so. But with those older traditional detectors, as we decrease the processing time, the resolution tended to go up. Whereas with our new detectors, which is the darker line, as we decrease the processing time, the increase in resolution is much smaller. So we refer to this as sort of a resolution stability function. And so what that means is we want to use smaller, shorter processing times, because that allows us to process more counts. And that's what we see on the right there. As the curves go higher and higher into the red and yellow curves, we're using shorter and shorter processing times. We can handle more input counts there, which is what's shown on the horizontal axis, and those translate to higher output counts on the vertical axes. So with this new technology and these new detectors, we're able to do three things. We can bring in a lot of counts, we can process them and put them out as a lot of output counts, and we can do that with very good resolution values, even at high speeds. So why that's important for efficiency, EDS spectra can come down to statistics and counting. So if I look at a spectrum here from a quartz sample, this is a spectrum with 2,000 counts total. And we just increase this to 4,000. You can see that the background starts to smooth out a little bit there as we increase the number of counts in the spectra. And so as we look at this, we get more and more data. And if we look at the effects of this is a 2,000 count spectra. This shows the number of measurements on the horizontal axis and the concentration in weight percent on the vertical axis for the two elements. So we know what the concentration of silicon and oxygen should be. Those are shown as those two different lines there. And the dots are the scatter of the measurements around there. So we have pretty good accuracy, but our precision is a little bit off. We have a little bit of noise relative to the expected value. But if we increase the number of counts in the spectra, we start to get, and this way on the vertical axis now, this is the number of X-rays in the spectra. We can see as the longer we count, the closer those measurements start to get to the expected value. We lose this scatter. We get better precision. So to get good statistics, we really have two different approaches. We can increase the acquisition time, or we can increase the counts coming through it. And so we can increase the count rate or the throughput. And that's where the detector technology really helps us, is we can, when we get a high count rate, we can also get a higher fraction of process counts. Okay, now what do we gain or lose by fast spectrum collection? This is a curve that shows what I showed earlier, but on a little different scale. And I think this kind of, it can be a little bit misleading, that as we decrease the amp time, so on this chart we're going from a low amp time, a slower value on the left-hand side, faster on the right-hand side, so the curve's going up. And you see our resolution at our slowest amp times is there in the 123 range. At the fastest ones, we're up at the 136 range. You look at that curve, it looks like it's increasing quite a bit, but if you remember the earlier curve, this change is actually pretty small relative to older detectors. So even at these very fast amp times, this resolution is still very good. And so we can look at this on a spectrum. These are spectrum that are overlaid, collected at these different amp times. We zoom in on a peak here. You can see as we increase the amp time, we get a little bit of peak broadening, but it's not a pretty significant effect. And so that's the broadening there. And if we look at this at the, this shows the time to acquire 1 million counts at 30% dead time. As we increase the amp time, as we decrease the amp time, so I'm going from left to right, we can get the same amount of data much, much faster, but we're still getting the correct concentration measurements. And that's because of statistics. We're getting good counting statistics and really no loss of quantification accuracy or precision. This also translates to mapping, of course, and so this is just an example of beryllium. The fastest amp time we can go with good beryllium, or boron, sorry, I see a B and I say beryllium, but that's actually boron, is the 0.48 setting. We can get at this, keeping the dead time constant 25%, gives us about 10 times more data throughput than at the slowest amp times. That translates to better looking maps at similar conditions. So these are heavier elements that if I look at it with the moly and the boron, you can see that with the faster processing time on the top, the moly and boron maps jump out with a lot more data, a lot more contrast. And of course, this EDS performance also translates to simultaneous collection. With EDS and EBSD, we can tilt the sample and synchronize and collect the data simultaneously. Having these fast detectors means we can get a lot of counts in and under EBSD conditions and get a lot of counts out. And of course, when we simultaneously collect these, we get direct spatial correlation of both measurements. And our software has very good high tilt quantification measurements available within the software. So we can operate the EDS detector at the same maximum speeds we can operate the velocity super camera. So this is an example of a microelectronic part where we've scanned it at 4,500 points per second and collected the chemistry. This is an interesting one because you can see there, if you look at this, it's looking from the left-hand edge, there's some small grains, large grains, and then sort of a medium grain size range, and then it repeats itself on the other side. So if we look at this, this is an example for where we want to use simultaneous data. There's a copper phase and then an iron nickel phase. They're both FCC, so when we try to differentiate those crystallographically, there's a loss of abilities. They're not easy to differentiate because they both have the same interplanar angles. So our phase map there on the right is very speckled between the two, but obviously the chemistry is very distinct of where these phases are. So we can use our chi-scan functionality, which uses EDS to drive the phase differentiation, and then uses EBSD to determine the orientation. So on the left, we can determine the phases correctly. We see the copper on the outside. We see the nickel on the inside. Then we can get the grains calculated for each phase correctly, and we can look at the grain size for each phase. And this is just important because the copper phase has sort of a bimodal grain structure, whereas the iron nickel is more of a single type distribution. So without using chemistry, we couldn't really accurately differentiate all three of those easily. The next thing I want to talk about is our new APEX software. APEX is the next generation data acquisition program that we've developed for EDS, EBSD, and integrated collection. And really from the ground up, it's been designed for efficient operation, both for new users and for experienced users. And part of that for efficiency is having a consistent workflow and data structures for both applications. So if you learn something on the EDS side, it translates very well over to the EBSD side. One of the foundations of this is, of course, the user interface. We've gone to what's called a ribbon bar design, very similar to what you'd see in something like Office or MATLAB. Tried to make icons both graphical for easy recognition, but text to describe what they do, to provide a feedback on what each button does. Functions all organized into task-specific pages. This makes it easy to find things, makes it be able to do what you want to do, and you can learn the program very quickly. Like I mentioned, they're very similar from one to the other. So, the collect image buttons are at the same place, where we start things are at the same place. So it's very easy to transition from one way to the other. And in following that same theme, within APEX, we have our APEX Suite mode. So we have a button where we can run EDS, we can have a button where we run EBSD, and then we have a review mode. And so we basically can switch from one to the other very easily if that's the approach you want to use, but also have the flexibility of only running EDS or only running EBSD as independent applications, depending on what works best for your workflow. Of course, the primary goal, especially from the EBSD perspective, is to be able to collect maps with scanning. So within both applications, there's dedicated page, for mapping collection. There's a one-button start, just using the default parameters. But on the ribbon bar, there's easy ways to select things, easy selection of the step size, shows you the number of points, the estimated scan time. And the user interface is configurable. If there's certain information you want, you can adjust it to show that information. The other thing, of course, when it's mapping, there's some dynamic feedback. One of the important things we want to do is give lots of information back. So this just shows a screenshot of a collection where you can see, first you see the orientation map as it's being developed. There's that vertical stripe that's showing the confidence index as a function of each line. Lets us know if the indexing algorithm is working as desired. Then there's a strip there that we're able to select different grayscale and color maps. So we have a few different variants of the color to show orientation, to show phase, to show EDS. And then on the grayscale, we can show image quality and confidence index, SEM image and Prius type imaging, and you can dynamically adjust those. And I'll show a slide on that here where I've gone and selected the Prius, and I can select which area of Prius we want to show. And that changes dynamically while you're mapping. We can also do things like see the cube, see the Huff transform, see the pole figure, just to get an idea of feedback of how the system's working, how it's progressing. We see similar things on the EDS side. So this is a screenshot of the EDS mapping, where in this case we're seeing a phase map. We can see the elemental maps. We can see the spectra. We can adjust the phase tolerance if it's doing its phase classification routine. And we can compare to a lookup phase library. So it matches against a library if we want to do that. And we can also do some interactive things where we can go in and draw an area in the image and exact spectra while it's collecting. We can add and remove elements from the display. We can show elemental maps for just the individual phases. So there's a lot of dynamic things that can occur that lets you understand things while it's going. You can also go from collection into review mode. Line scans, this is something we're put in that's for EDS and for EBSD. We can go in and get quick information. That's why I selected for efficiency just across the surface. So this is looking at across some grains of material, just looking at the EDS data across a line profile. That EDS data can be shown as net counts or composition percentages, weight or atomic percent. And then, of course, one of the big things for efficiency is the ability to do batch mode operation. And this applies to both EDS and Ebsd or simultaneous collection. So we can set up collection, record it to a batch list. We can adjust the magnification, the scan area, the step size, and add it to this batch list. They can be maps. They can be combo scan maps. They can be EDS point collection. They can be line scans. Whatever the list you want to have. So basically you can set up this recipe, go to different areas, go to different samples. So you can have more efficient use of your SEM through this automated collection, which ties in well with these faster detectors. You know, there's times the microscope's just sitting there, you can take more advantage of that. And then for learning the system, we've put in some features that help set up the system for different types of operation. So one is what we call our smart camera optimization. You know, with the camera, the Ebsd camera, we can set, you know, the pixel resolution through binning. We can do full pixel resolution, or we can bin the camera down to smaller resolutions. Generally, we bin it down smaller for faster data collection. So that's one variable. We can often adjust the gain on the camera. We can adjust the exposure time. And so you have these different variables, and you know, part of the learning the system is knowing how to adjust those. But one of the easiest ways to start learning is using some of these context-sensitive options. So you can see here, here are a few of the different pull downs. So they're pull downs if you're trying to map, or pull downs if you're trying to just collect individual patterns. So you can do one that's a reduced noise. You can do one that's fast. You can do one that's ultra fast. In this case, we have one for what we call atom probe assist when we're looking at a transmission type sample. And we have one for EDS. So we'll look at the EDS count rate and say, based on the number of counts we go in, you probably want to use the camera at this speed to get good statistics, like we talked about earlier. And same thing for point collection. We can set it up for the best pattern, a standard pattern for the EDS quant. Really where these are useful is it makes camera setup reliable and fast. And it also provides feedback of what it's doing. So you're able to learn, so if you want to manually tweak it. So, you know, users, the learning curve for camera is pretty easy. You can just select one of those, press it, and it sets up the camera for you. Similarly, we have an area where we select the step size. So when we collect an image, we collect it at a given magnification, and we have these defaults of a coarse, a medium, and a fine pixel resolution. If you look at the graphics on there, it may be hard to see, but the pixel density of the sampling array changes on the icon. And so it will select an appropriate step size based on the selected magnification. And it's designed for different cameras. So if you have a slower camera versus a faster camera, these definitions change a little bit. But it helps for consistent measurements across multiple scans. So if you always set up at, say, 500x, medium resolution, your step size will be the same for each scan. And the reason that can be important is when we talk about looking at misorientations within a material, oftentimes your misorientations will be measured as a function of step size. So if you're comparing two samples, it's good to have a consistent step size, or comparing two areas. It makes it more of an apples and apples comparison. So we found this step size selection is very useful for that. And so this type of information is also shown on the batch setup list, so you're aware of what step size is selected for each one. And then, of course, for efficiency, one of the important things is easy data management. And so with Apex, we can save the data where we want to save it. We can specify the drive and the folder and the file name. We can name it whatever we want to name it. We can move it where we want to move it. Certainly on the Ebsd side, it's pretty common to move your data to a remote computer for analysis. So we're able to save this to a single file that allows us to, you know, it organizes the data but makes it portable. It's project tree based, which is an intuitive way of structuring data. Provides default names, as you little example, the first set there into area 1, we have an Oim map 1, 2, pattern 1, 2, 3. So pretty easy names, but on area 2, I've gone and named these for what I wanted to call them: deformation zone, base metal, nickel pattern, titanium nitride pattern. So you can rename the defaults if you want. And then these can be used with the review tools that are accessible for analysis away from the SEM, which means you don't have to use up valuable SEM computer time. You can go to a remote workstation to do that. And our software is designed for that remote work away from the microscope collection. And of course, I'm going to talk now about Oim Analysis. This is the review tool that we use to process the Ebsd data. Oh, clicked one too early there. And so, sorry, that's the one I want. So, you know, it's important to recognize, you know, oftentimes when we're talking about Ebsd systems in a commercial perspective, there's a lot of focus on the detectors. There's a lot of focus on the acquisition software. But really, it's in the analysis that a lot of the information and the science is done. And so that's where we really emphasize Oim Analysis. Sorry, this slide must have a timer on it because it keeps moving on me. And so Oim Analysis really provides a large range of tools for visualizing, analyzing, describing the microstructure. And it's a tool that does that. So, of course, the flip side to having a very powerful and comprehensive package is there's a lot of features and functionality. So the challenge we've had is how do we make this accessible and make use of this efficient? One of the first ways we've tried to do that is through what we call our Quick Gen Toolbar. This is one of the toolbars that's available in the software. It offers one-button access to the most common maps, plots, and charts, and we'll go through what comes out of this. There are also buttons that can be user-defined for individual maps, individual plots or charts, also partition and data set based buttons. And I'll describe a little bit what those are as we go forward. But users can add custom things to this toolbar. There's access to what we call confidence index standardization. This is a common processing we use that doesn't change any of the data, that helps extract the most reliable data. And then it adds access there to our template list for easy access to templates. And I'll talk a little bit more about templates and some of the efficiency gains that can be brought there. But really, it allows for a one-button analysis. So on one level, you know, within Apex, there's, you know, a one-button type collection, one-button analysis, and really a one-button reporting as well, as we'll talk about. So the workflow can be very easy, but there's a lot in depth that can be extracted as well. So on the Quick Gen Toolbar, I just kind of want to review kind of the most common maps in case you're not familiar with Ebsd. There's our orientation map. These are the most common type of maps I think we see with this, where the colors shown correspond to the crystal orientation. And so these are showing here, like red grains will be 100 orientation, blue will be 111 orientation. The image quality map shows the quality of the pattern, and so the brighter the points, the better the image, the darker the less. So we see a lot of grain boundary contrast. Grain maps show grains as color. They're randomly colored to show size and morphology. The grain boundary map overlays misorientation values as grain boundaries. So we can see specific boundaries as regular boundaries, high angle boundaries, low angle boundaries. Sorry, this has a timer on it and driving me nuts. So we can show low angle boundaries, high angle boundaries, mid angle boundaries. We can also do twin boundaries. All these can be adjusted easily. Then we have our kernel average misorientation map. This is a map that shows basically the local misorientations present after plastic deformation. So in a partially recrystallized steel, we see there are some grains that have no misorientations, and then some that have quite a bit. Those are the deformed areas. And then we have our phase map. And this, of course, if we have multiple phases we've analyzed, we'll show different phases in different colors. So this shows quartz, olivine, and enstatite in a material. And if we have EDS data, our EDS Quick Gen maps create an EDS color map for each of the elements that we've activated. In addition to these maps, we have our QuickGen pole figure, so we can show a pole figure and an inverse pole figure. So the pole figure shows your common planes, that's your 001 plane, and your inverse pole figure will show versus a reference. So in this case, it's the surface normal. So this can often show a quick idea of any preferred orientation or texture that's present through clustering. And then we have a quick grain size distribution. So we get a chart of the grain size. Of course, it also provides the grain size statistics, the average, the standard deviation. And we can see our misorientation angle distribution. This gives an idea if there's any kind of a grain boundary texture. Like in this case, the peak near 60 degrees would be a number of twins. Now, all these maps are just different types of map outputs, and those are those the most common ones. But everything in the software, each of these individual components can be basically specified or customized. And so this is just an example through it where if I want to select a different color scale, I can come into the map properties, go to my color code pull down, and there's lists of them. And one of the things I think makes it more efficient is these are sectioned into different things. So there's some scalar measurements like image quality, fit, confidence index. There are orientations to show our inverse pole figure, crystal directions, quaternions, Euler angles. There are grain size information, so diameter or area or ASTM number. Then grain shape. Are they elongated? Are they equiaxed? Are those aligned in a certain spatial direction? There are grain average values, and then there are a section on local misorientations, the CAM maps or the GROD maps or the local orientation spread maps, as well as some other sections. But there's some organization to do that, and that's the same for maps for the plots and charts as well. I mentioned earlier templates. This is an important concept that can save a lot of time, because if you do start customizing some of these different preferences, you can save them as a template. And so here, this is just a schematic of I've set a grayscale, I've set a color, I've set boundaries. I save that to what we call a template file. And these files are saved, and they can be shared, and they can be used on different levels. So I mentioned earlier, we have a partition level, so that's within a sample. So I can have, this one has a confidence index and an all data. We can have a data set level, so it applies to the entire data set, all the partitions. That's useful if you have multiple phases, and also to a project level. That would apply to all the data sets within a project. They can also just be single entities. So these templates can be applied on any level of the project tree, which gives you a lot of flexibility if you're looking at one sample or many samples or in situ samples. You can target this template type of analysis. And that's also very useful because we can take these templates and we can load them into our file and find them from the QuickGen toolbar. So this little area here where it says Apply QuickGen Template, this provides a pull down of the different templates that are available. And you can see, again, these are sort of organized by different ones. So again, from the QuickGen bar, you can pull down and get a full descriptive analysis that you can use that to generate your data very easily. We'll come back to where else we can use this in just a second. These templates can also be used for actual reporting if you want to just get a report out. So this is a new approach we've used. It's really, I'd say it's ideal for customers with repetitive analysis. If you're doing similar type of samples or want similar type of outputs, having a report based on a template makes it very easy. And so, basically what we need to do this will go through what's done in Apex and Oim Analysis. We can use it in both places. But the first thing we have to do is define the template. We talked about that earlier. So in this case, I've just created one that has a lot of the show things I've shown you, a CAM map, a grain map, an IPF map. a Prius map and an image quality map. We export that as a template, and that's just a template file. We then go into the report layout, and we select that template. It provides a list of all these map outputs. We can use the report designer here to go and position the different maps however I want them. So I can define location, I can define size, I can put in the legend, we can put in a header, whatever you want to do. That you can say, for these different map types, this is how I want it to show up on my page. We save that as a layout. Then we just basically run the report for any given scan with the selected template. So once it's set up, or once you've selected the template, then step 4 is the only one you need to use. And so you'll generate your report as a Word file. That's what's shown here on the right. And the really useful thing here is it can be used both within Apex or Oim Analysis. So if I am collecting a data set and I know I want to report from it, I can just click, send a report. And at the end of the data set, it will run Oim Analysis automatically in the background, use the template to create the images, and put them into the report as defined. So you can use that for a single scan or even for a set of scans. You can use it for the batch scan and create a full report, basically with the click of a button. So that's a pretty easy and efficient way to go from start to finish and to have an output that you can give to somebody. Now, the other step of this is we have what we call our batch processor. And we have batch processing available in both EBS review and EBSD. The EBSD, the batch processor, is in Oim Analysis, and it's designed to do both custom processing and analysis of EBSD scans. And it's ideal for work on repeated type of samples. If you collected, scans from 10 different samples of the same batch, or in situ work, or whatever, batch processor lets you consistently analyze these, and it's beyond just creating maps. I kind of wanted to walk through what it would do. So when you use the batch processor, you're able to come in and just select the files you want to look at. We can look at tens, we can look at hundreds of files all in the same batch, and then we get our batch processing window. And so it's a full suite of tools that's useful for this type of analysis. There's full customization of which you want to do and the settings of those, and you can load and save these batch processing parameters. So if you say, here's what I want to do for this type of work, you can save it so you're able to remember it the next time and not have to recreate it, which helps for consistency. So I just kind of wanted to review some of these because these are ones that I've used. I use them quite a bit when I'm looking at samples. Oftentimes I'll get samples from people and they'll send me 3 or 4 samples, so I collect a scan from each one, and then I want to process them all the same so I can show comparisons. The first one's an alignment tool. Obviously for alignment, they should be spatially or temporally related. So if we've done in situ heating or in situ deformation, we use the alignment tool. If we've done 3D serial sectioning, we use the alignment tool. And in this case, it uses orientation and or pattern quality information for the alignment. And that's really important because, on your EBSD surface, oftentimes there's not a lot of contrast. So sometimes, people use fiducial marks and things to create alignment. In this case, we're able to use the orientation of different grains, which usually provides enough varying information that allows for very easy and consistent alignment across a series of data sets. We have a crop function. Again, if you've done in situ work, oftentimes between scans there can be a little bit of shift. And so if you're aligning this image stack, you can have areas that only have area for one or the other, and sometimes that will show up as black. So we have a tool that allows us to come in and crop, so we're only showing the area that's consistent throughout that data cube volume. A lot of times that's for aesthetics, but it's a lot easier than doing it by hand to do it as a stack. There's a cleanup routine. Of course, with this, there are a library of different noise reduction cleanups that we can use. We have a tool that lets you select up to 3 of them, so you can run them in a sequence. You can edit it and set up the parameters you want to use for that. And then we have a rotate as well. We have the full 3-dimensional orientation data. Sometimes we want to represent things in a specific reference frame, so we can do up to 3 rotations where we specify the axis and angle of rotation. Again, when you're doing this with multiple scans, it's very nice to do this as a consistent batch so that you don't forget one and have one that's difficult to compare. This next one, this is a feature to convert from a hexagonal to square grid. Our sampling is hexagonal by default to give us 6 equiax neighbors, which leads to better misorientation type analysis. But often, not often, but there are times though that other data processing packages don't support it and people want a square grid. So we have a little converter that goes from hexagonal to square. Again, that's really convenient when you run into the problem. Here, I went one too fast. This is where we decide if we want to use a template again. So you can see templates are used many different places, and batch processor is one of them. And we can select all levels of templates. But really, I wanted to point out at this stage, you know, this tool doesn't necessarily have to be to create images and do analysis. You can see there's lots of other tools that can be used just to process your data as a batch. This is an export. This is if we want to create the images. Where do we want to save them? Do we want to save the legends? And then we have the data. This allows us to what we're going to do with the data. So we can select if we want to save the data after processing, in what format do we want to save it? Do we want to save it with the huff peak information or the EDS or the patterns? Do we want to save everything as a final project? Do we want to save them as individual projects? Do we want to export out data individually? All these things are possible. So again, this is based on a lot of experience with users of, hey, we want to be able to do this, and then we wanted to be able to do it on more than one sample at a time. We basically built it so you can do it for one sample or you can do it for a batch of samples. And when you have a batch of samples, you start loving the batch processor. Another thing we do in Oim Analysis is our reindexing. So if we've saved either huff parameters or huff peaks or saved patterns, we can load this data back into Oim Analysis and reindex, recalculate orientations. And that's really valuable because what it means is we can collect a set of data on the microscope and then take it offline to do reprocessing. You don't have to spend a lot of microscope time where you might be paying by the hour to collect your data. You can come offline and really start to work through it. And if you've saved your patterns, you can do things like adjust your backgrounds, adjust your huff band detection, adjust your phases, use EDS for chi-scan, apply NPAR. So there's lots of different things you can do that saves you time away from having to do this tweaking when you're live on the microscope. And this reindexing is also supported with batch processing. So if you want to do a batch set of reindexing or a batch set of chi-scan with the same settings, you can set it up and do multiple samples at the same time. So yeah, I think you can get the impression that, you know, we put a lot of tools in that are very valuable, but to use it for a set of materials, if you can do it all at the same time without having to go and set up each one, becomes even more efficient. So that's why a lot of the emphasis of this talk is on this batch processing. This will be a funny one to anyone who's ever seen me give a demo, but as you're creating these different maps, you know, by default, they're all displayed as an image stack. So you can start to get lots of maps. And if you start getting a lot of them, it can be a little bit tricky to pick out each one you want to see and show it. So the toolbar has some very nice tools to help manage these images. So this is just a little section of the toolbar here. Going from left to right, there's a button to cascade them, to put it in that cascade view, to vertically tile or horizontally tile them, and then to close all the windows. So I've selected here a horizontal tile, and you can see that stack has now been made an array of images. So it automatically fills your monitor space with those images, makes it easier to see them all at once. If I want to go back to the other view, I can click the cascade view. If I want to close them all, then I can come and just reopen the one that I want from the project tree where it's listed by name. And so it's a really nice way of generating a lot of maps and then saying, here's the ones I want to see, here's the ones I don't want to see. And so I use that all the time. You know, this is something that's important the smart data loading, as we get faster and faster cameras, we're getting more and more data. And so for the analysis, sometimes we don't need to load all the data initially to show what you want to show. So in Oim Analysis, it sort of smartly loads things now. So it brings in Huff peaks, saved patterns, EDX, grains, grain size on an as-needed basis. So it doesn't do a full calculation of all these things right when you start. It's sort of as you go in the background, and then as requested. Which means if you're not needing these, you can get to what you actually want much quicker. This is a function I think is really useful when doing many things. So you can see there's a crop, merge, rotate, cleanup, coarsen. Whenever we do something, there's options that says I want to crop in place, I want to crop and add to the project tree, or I want to crop and export as a new data set. And you can still add to the project tree. And the reason I really like this function, I think it ties into efficiency, is, there'll often be a question of what does this do? How's it affecting my data? What's this cleanup routine doing? Am I rotating the right direction? Did I crop the area I wanted? If I crop and add it to the project, you have two sets of the data, but you can easily compare the before and after to see if it's what you want. And the summary of the data set will record the functions you've done, so you can kind of see a trail of any processing you've performed. And so, to me, it's an easy way to see the effects of these things and decide, is that really what I wanted to do? The other thing I think is really useful is that within the project tree, you can copy and paste between nodes, and this can be done on a data set level, partition level, or within a partition. And again, this helps keep things custom. So when I'm doing just things day to day and I'm not worried about saving a template, but I want to do the same thing from one sample to the other, I can just copy and paste an analysis, and it just repeats itself very quickly. And this is another thing here. You can just drag and drop files from, say, Windows Explorer into the project tree, and it'll open the files and multiple files all at once. So it's a quick way of things. Rather than having to go file, new data set, you can just drag it into the project tree and it will open. It can also work with double-clicking the data set just in the Explorer with a single data set. So it's a quick way to get started. This is just an example of an aluminum friction stir weld. Right along the weld interface here, and if we look at the orientation map in the center, you can see basically there's some larger grains on the left and some smaller grains on the right. And so really with this sample, wanted to say, hey, I want to analyze the different regions. One's within the weld nugget, one's within the base metal, and see what's the grain size, what's the texture and orientation of the two different regions. The nice thing within Oim Analysis, it's very easy for what we call interactive partitioning. So on the left here, I've created a grain map. So the grain map, again, just randomly colors the grains. It's just to show size and morphology. In the middle, I've shown the grain size distribution. So you can see there's kind of two different peaks within that distribution. You can always go and select the number of bins if you need to change from 20 to 50 to 100. Sometimes that helps separate out different peaks in a histogram. But in this case, I've just selected and used our selection tool to say, I want to select the peak on the left sort of in blue. I've adjusted the color scale so that it gets close to the other peak. It becomes a lighter shade of blue. Then the peak on the right is red. And we can visually see now that the red grains correspond pretty well with the grains on the left and the blue with the grains on the right. And so once these areas are defined, I can say, let's take all those blue grains and create one partition. We can then say anything that's not that could be an excluded data partition, or I could use the red color as a definition. But we can create these different partitions within the full data set. And once we do that, then again, we can create the analysis of that. So this is showing the orientations of just the small grains, the orientation of the large grains, and then the grain size distribution for both. And so, sometimes understanding the subsets of different things helps analysis of what might be going on in your material, whether it's grain growth in a deformed material. Separating out those two different components allows for unique analysis. And of course, something like this, maybe we want to go zoom in to the fine grain area. This has a lot of data points. So there is a zoom feature in Oim Analysis, but this is also a crop. I can just go select an area and say, this is the area I want to pull out as a section, do analysis just on that and compare it to an earlier version. There's also useful functions with this for things like coarsen and merge. Okay, I like to just kind of mention the Oim Analysis help file. As far as for efficiency, being able to get the results you want, it's a great resource. You can view by contents. It kind of gives you a project tree type of an approach for what's in the help file. There's an index of key terms. You can search through it. There are step-by-step tutorials for key functions. So you can see there's grain size analysis, texture analysis. We talked about interactive analysis, templates, NPAR, Prius, chi-scan, batch processor. All these things I've talked about are all available through step-by-step tutorials. And there are even example data files that are included that are used in the tutorials. So you can work through and see exactly how to do this type of analysis. And beyond that, for further reference, the help file also provides a lot of detail into the calculations that are going back, as well as key references. So, if you're I'll jokingly say a student who's going to go and say, I want to understand the full, front to back process. This kind of explains, how we go from Euler angles to an orientation matrix, and a picture of, what a CSL boundary, sigma phi boundary would look like. And, here's a tensor for different deformation gradients onto the sample. There are pages and pages of a lot of reference material, but if you wanted to understand things in depth, it can help guide you through that with understanding exactly what's being done in the software. Finally, the last thing I want to talk about is new structure files, new indexing patterns from new materials, because this is something that's been tricky for a lot of people for a long time. And the question is, how do you get started with a sample that you've never characterized by Ebsd before? So of course you have to prepare your sample and get some patterns, but then you need to build what we call a structure file so they can be indexed. So we need to know the crystal symmetry, the lattice parameters, and then most importantly for this discussion, which planes are going to diffract, and we call those reflectors. And so generally there's been two ways to create this. There's one where we call it the HKL method, or the plane method, where we specify the symmetry and lattice parameters, then we enter the most likely planes. And usually these are, it's the low index planes, generally the ones that scatter the strongest intensities, but there's some rules to that. So we can put in a list, but the key thing there is the one on the bottom, which is optimized, where there's some manual verification and adjustment. The other way to do this is through what we call the atomic position method, where we use the crystallography and the atomic positions to then calculate structure factors and then auto-activate the most likely reflectors based on the highest intensities. But again, even in that step, there's often some optimization that's required. Why do we need to optimize? Diffraction models aren't perfect. And so the kinematical models we've used previously don't always match perfectly the observed patterns. If we've used X-ray diffraction databases, X-rays diffract a little bit differently than electrons. The observed materials may be a little bit different than the one in the database. You can have atomic substitution, solid solution issues. And sometimes the reflectors, the key reflectors we want to have in our structure file are the ones that are going to be detected with the Huff transform. If we're getting too many or too few, that can both lead to some issues. So to optimize this, generally, before we've used this kinematic simulation, where we put in the coordinates of the atom positions, the scattering factor for the element, and it calculates an intensity of a given plane. The trick is the kinematic solutions don't often, fully resemble an experimental pattern. We know that's the case, and we've sort of lived with it up until now, where we've introduced what we call our Oim matrix dynamic diffraction simulation package. This is a package that allows us to do a number of things. We can do dictionary indexing. We can simulate patterns. But the key things I want to show here is the little red box in there. There's a little button there on our structure file builder that says optimize our structure file. And so on the left there is where we then put the crystallography. So we kind of give it a name. We put the composition. We select the space group. We select the point group symmetry. We enter the last parameters. We enter the atomic positions. When we do that, it uses symmetry to show our equivalent position. So that's an area that makes it easier. And then once we have that information, we can hit the optimize button that allows us to come to our next page here, which it will run through and use these dynamical diffraction simulations to auto-optimize the structure file. So it does that by simulating, multiple patterns of different orientations. So you can kind of see there in that screenshot in the middle, there are lots of different dots showing the different orientations that have been sampled. And so it can use these simulated patterns to determine the diffraction bands of highest intensity using a more accurate diffraction simulation using dynamical diffraction to create a reflector list. Additionally, from that, we can take these simulated patterns and run it through the indexing engine. And so with that, we can use the different Huff parameters to not only simulate the pattern and intensities, but we can also see how those patterns will index. And so in the end, we can say, can we tweak our reflectors and our indexing parameters to optimize our indexing performance? And that's what we're able to do with that. So compared to traditional point-and-click selecting reflectors by hand, this almost becomes a 1 to 2 button type of analysis to create these structure files. So it's much easier than previous approaches. So in summary, first of all, our detectors provide the fastest collection speeds, the highest throughputs, the most efficient data collection. The Apex software provides, an easy-to-use interface and a feature set designed to get good data quickly. And I really emphasize the good because it's not just get data quickly, but, the checks in there to make sure things are set up appropriately so that the data you get is good data and be able to get it quickly. And then Oim Analysis is really a powerful package that has a lot of tools for quick analysis, but also easy, powerful analysis. And then all these components can be tied together for use of batch collection and analysis of data. And so with that, I'd just like to highlight, there are a number of additional resources that we have at EDAX. The webinars we have are recorded and archived on our webpage. We do a blog where we have a lot of very good content that's available at the edaxblog.com. We have some different movies we put together on YouTube. We also have those on our website. We have posts on LinkedIn and Twitter. And if you need to reach us, we can be reached at info.edax@amatech.com. And then as a plug for next month, Sean Wallace will be talking about understanding and troubleshooting the EDAX indexing routine and Huff parameters to understand how we tweak different things in the indexing engine and how that reflects your results. So I encourage you, if that's interesting, to please register for that. And with that, I'm going to say thank you very much, and I will try to answer a couple of questions. There are a few here. The first question on the list says, what EDS detector was used for our simultaneous work? In this case, I was using the Octane Elite Super, which is the detector that has the 70 millimeter squared detector. We have another question, which is how to do chi-scan. That one's going to be harder for me to answer now. We generally do that now in Oim Analysis. Oim Analysis 8 has that put into it. There's a tutorial in the software to do that. Prior to that, we would do it in the data acquisition team package, but we've tried to put it as more of an offline package for that. There's a question here of is Apex a replacement for Team? Yes, that's where we're going. And there's another question, the difference. So, basically right now for Apex we'll be replacing team for EDS and EBSD analysis. The biggest there's lots of differences, but the biggest thing is trying to make the functionality easier to see through the user interface, making the data structure easier to understand and manage, being able to, again, specify where you're saving it and what the name you're using it. And of course, it's a package that's, I say of course, I did a webinar 2 months ago, so it's of course to me, but it's a 64-bit application. So it's really designed to handle larger data sets, to use, modern computers, modern processors, and be more efficient in operation, be more responsive. And so with that, I think we're at 10 o'clock. There are a few more questions, but I think in the absence of time, we'll probably stop. If you've submitted a question, I didn't have a chance to answer it, I'll respond to you offline shortly. So thank you very much for your attention, and I hope you found something useful from it. Thanks.